In the previous chapters, let's see. We covered elementary steps. Remember, an elementary step only has one transition state. So when you're looking at the energy diagram of the reaction progress, you're going to see reactants and products. I don't know, put them over here. And you're only going to see one transition state. Right? This is characteristic of elementary steps. And this amount of energy is required, activation energy is required for the reaction to go. When we start talking about multi-step mechanisms, we're still interested in the elementary steps, but we're combining them. So their energy diagram starts to look a little more complicated. In other words, you start off with reactants and products, but you might go up here and then go up here, and then you end up there. So you go through multiple transition states with more than one elementary step involved. Okay. Now, of course, the step that takes the most energy to get to its transition state is the rate determining step. Remember kinetics in general chemistry? Okay, the rate determining step is the slowest one. It's got the highest mountain to climb. And typically in these multi-step mechanisms, the first step is going to be the rate determining step. I suppose that there are possibilities where it could go up like this and down here and then go way up here like that for the second one, but I haven't seen it yet. All right, so for our discussions today, this type of scenario is characteristic of the SN2 and the E2 reactions, elementary steps. And we're going to introduce SN1 and E1, these are elementary steps, these are multi-steps. You still got the nucleophilic substitution and you have the electrophilic elimination. But it occurs in two steps. And we're going to find out how to tell the difference when you see the reaction data, how to know which one is which. Okay, so just as a reminder, for the SN2 reaction, you have a nucleophile attacking the substrate on the carbon, and there's a leaving group on the carbon that during the process, during the reaction, the leaving group leaves with both electrons from the bond. It has to do that because, let's see, what are they using? They're just saying leaving group. Okay, so it could be chlorine, could be bromine, or typical. And then you have a nucleophile, which has a lone pair. And in this case, they're giving it a negative charge, but it doesn't have to have a negative charge. What it does is when it attacks here, excuse me, there's one more. These are hydrogens. Actually, they could be anything. I'm going to make them hydrogens for now. When it attacks there, and if you try to add two electrons here with a nucleophile forming a bond, you exceed the octet. Right? So the only option here is for this one to take its two electrons and leave. That's probably why they made this one negative, so the charges would balance. So that's the SN2. It's a single step reaction. It's an elementary step. For the SN1, you get the same product, but you go through two steps. So let me draw them separate so we can compare them. And so we have this. You have the leaving group. You have the nucleophile, which actually doesn't come along yet. So the first thing that happens is this leaving group leaves. I'm gone. So you end up with, right? If we take those 2 electrons with us, what does that happen? What does that make the carbon? A cation. Okay. So that leaving group has left. Now what do we have? Now the nucleophile comes in and attacks. It's a 2-step process. That's why it's not elementary. So the nucleophile now, they put the nucleophile on this thing right here, on the arrow. Now the nucleophile attacks the negative, attacks the positive. And we end up with the same product. I didn't draw the product over here, did I? So we end up with the same product for the SN1. Now, remember what the 2 and the 1 stand for. This is the molecularity of the reaction. And in kinetics, we can talk about the molecularity of elementary steps based upon how many reactants come together at once. Right? There's only 1 here. That's why it's SN1. It's a nucleophilic substitution, but it's only molecularity is 1 until you get to this part. But in the beginning, the slow step, right? This is the slow step, is SN1. A singular molecularity, whereas this one is a bimolecular, right? Both of them are involved in that process. Okay. I'll move on if it's okay. So far? Okay. Now, if we want to talk about the overall reaction is still nucleophile attacks the electrophile, and we get a product. The overall reaction is exactly the same. And if we set it up like they did in that slide, where you have the SN1 step where the leaving group leaves and then the nucleophile attacks, then when you add those 2 steps together, right, the intermediate, the carbocation, cancels out. It's like Hess's law, where you add your reactions together and you want to get this reaction down here, so you add these together and you get things canceling. It's the same concept. The nucleophile, the carbocations cancel out in the overall reaction. So it's typical for kinetics when you're trying to devise a mechanism for a reaction that the intermediates come and go so fast, you can't access them in real time. Right? So this is all theoretical. Now, there's some scientists that are working with lasers and things like that. They can actually see on the femtosecond scale things happening. But for us poor college instructors and students, we don't have that option. So we have to go back to the old school. All right, so that's the overall. So if I threw several elementary steps at you, theoretically, and ask you for the overall reaction, you know how to add them together and get the overall, because bring things down that are unique and cancel things out that are one on one side and one on the other. Hint, hint. Okay, so there's the SN1 reaction. It looks more like this, where you get the leaving group leaving, and that gives you an intermediate that's slightly stabilized. Notice that its energy level is less than the transition state for step 1. Now, it's still less stable than the starting reactants, but it's more stable than the transition states. It goes into a dip. And then the next transition state is where the nucleophile attacks the carbocation. And that leads you to your overall products. All right. So for the E2, we have this Lewis base, which very often is a hydroxyl, or it could be a bromide ion or a chloride ion. Those work too. But this base for the E2 reaction, the way we studied it before, I'll write it up here, give myself a little more room. We have this, what's the outcome of the E2 reaction? It's a pi bond. You add a pi bond between two carbons. So if we have this base, this Lewis base, and yeah, we're saying it has a formal charge of 1. And then we have a single carbon-carbon bond, and then other stuff. We have to have this hydrogen over here in order to make the reaction go. And let's see, then we have a leaving group on this side. So there's a leaving group on the second carbon, there's a hydrogen on the first carbon, and we form a bond here. And then these two electrons have to go somewhere. They can't stay out here by themselves, so they go here. And that gives you that, and let's see this. Oh, sorry. There we go. And this, and then the leaving group. Okay, so that's the outcome for the E2 reaction. Bimolecular elimination. Okay. So we end up with a double bond. Now for the E1 reaction, the first step is like the SN1. The leaving group leaves. Right? So we have this carbon-carbon leaving group here, 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 and hydrogen there. That one leaves. Right? So we get another carbocation. Yeah, we get another carbocation. So this one is still sp3 hybridized, but this carbocation now becomes sp2 hybridized. It's important to remember that because this is tetrahedral. Right? It has the three-dimensional tetrahedral structure. This one is trigonal planar, which makes the backside and the front side accessible to anything that wants to attack it. So where we're headed with that is stereochemistry. What do you end up with? All right. So we have this one plus the leaving group. Okay. I can do better than that. Hold on a second. There. Now, the Lewis base attacks that carbocation. No, it doesn't. Why did I say that? It attacks the hydrogen. Why does it attack the hydrogen and not the carbocation? Well, because we've specified it's an E1 reaction. There's a possibility, under the right conditions, that Lewis base could attack that carbocation instead. But in the E1 scenario, right, this Lewis base now attacks that hydrogen. Okay, so when it does that and it leaves the electrons here, they have to go somewhere. So they go over here and form that double bond. And when they do that, now this, both of them are sp2 hybridized. All right, let's see. So it's just these two together, right? Yep. So we've got those two together now. Form that plus this. It's like I often tell my general chemistry students, nature just does what it does. So this is the outcome for a reaction, and we got to explain it rather than trying to say, all right, in my world, it would attack that carbocation and we get something different. No, this is actually what we get. So we got to explain it. And this is how we explain it. So this is molecularity of 1 because the slow step is unimolecular. Whereas this one, the E2, is bimolecular. This, and when we say that, think in terms of concentrations. What would happen if we change the concentrations of the reactants? And this one, if this one has a different, we change that concentration and we change this concentration, then both of them are part of the kinetics. But if we change the concentration of this one over here, it's not part of the slow step. Right? So this is the only member of the kinetics. Remember the rate laws where you say rate equals some value here, and then we have A to its I want to say power, but that's not the right name. Order, to its order. Okay. And remember, when we're talking about general reactions in kinetics, this is experimentally determined overall. But when we talk about mechanisms, we can infer a rate law for each elementary step from the balanced equation. Right? So in this case, if we went from here, like that one, well, I don't know what we're going to call that. They don't give it a generic name. We could say this is some reactant to the first power because its coefficient is 1. You can do that for elementary steps. You can't do that for overalls. Brings back nightmares.
A little bit. I think once you get like the rate stuff, it makes more sense. But I think for me, it was a lot of just I had to end up memorizing.
Yeah.
I don't know. It was definitely tricky. I did not like that stuff.
No, no, you're not alone. Yeah.
Like all of that, it just got it definitely got me.
We just got through in my, I'm teaching second semester chemistry at the Raleigh campus. And we just got finished with our kinetics lab. We have to figure out what do I do with that data. And actually, most of the students are they're coming along with it. But it can trip you up. Okay. So one thing else you'll notice is, no, I'm getting ahead of myself. Hold on a second. So we got the SN1 and the E1. The overall reaction is going to be the same for both of them. SN1's, SN2's, same overall reaction, different mechanism. And the slow step again is the one with the steepest. Right? You gotta get that much energy in order to get to this first intermediate. So that's the slow step. The first one is the slow step, where the leaving group leaves. Now, in my world, that would have to be an excellent leaving group. In other words, very stable as a negative ion. So I'm thinking that once we understand how these mechanisms work as a synthetic organic chemist, we should be able to design the compound so that we have a leaving group that prefers E1 over E2. All right. So here are rate laws. And I write them just like this. When we have a bimolecular situation like this, then both concentrations are part of the rate expression. But if we have a unimolecular situation, only the slow step, the first one, that concentration or the substrate concentration determines the rate law. So the best way, the easiest way to memorize that is if it's a 2, the rate law has 2 concentrations to deal with. If it's a 1, there's only 1 concentration to deal with in addition to the K. I didn't know, in case you didn't notice it. Now, the nice thing about that is when we run rate experiments, you can look at the rate values you get from each experiment. Remember the method of initial rates, where you hold everybody constant when you don't change the rates from this experiment to that experiment. Concentrations. You don't change the concentrations on anybody except for one factor. So if you have 3 reactants, yields products, then you'll hold these 2 constant, or you'll have experiment. You'll have experiment 1, 2, and 3, say, and you'll have a value here, and a value here, and a value here, and then you hold this. These would be the same for the next experiment, but this one will change. I should have started at the other end of the alphabet. Change your concentrations. That's the way you do initial rates. And the number of experiments you need depends on how many reactants you have. So if we have 3 reactants, it's N+1. So you have 4 experiments so that you can get all possible combinations where everybody doesn't change except for 1. So the next one, we'd hold that one constant, maybe let this one change. Right, that's the way you use initial rates experiments. Well, if we look at the data for these reactions and we change the concentrations of the nucleophile and the substrate in that fashion, then we can tell which one it is. Is it SN1 or SN2 or E1 or E2? That's where we're headed. All right. We talked about rate determining steps. I don't need to hammer that one anymore. And of course, for Katie, it'll be fresh in her mind because we just got through that. Okay, let's see. So if we're going to write the rate law for an SN2, excuse me, we have to have both the nucleophile and the substrate with the leaving group. Concentrations are part of the expression. So that rate is going to be equal to some K times the concentration of the nucleophile times the concentration of the substrate. And since this is an elementary step, the orders are always 1. And the SN1 then only has, this is SN2, SN1, and because the rate is determined by the slowest elementary step, that's the only elementary step, so we're stuck there. But for the SN1, we have an elementary step where the concentration of the substrate is the only important one, because the nucleophile is not in the slow step. It comes later. It comes over here. This is the nucleophile attack. And this is the leaving group part. So it's the slow step. And that's what we're trying to show here. The energy barrier for that step 1 is very high compared to step 2. All right. I don't think we need to hammer this one anymore, I don't think, because well, this is SN2 and SN1, but we could do the same thing for well, might as well be complete. E2 and E1. So this rate is going to be, and these are different Ks, of course. This one is going to, the E2 is bimolecular, so it's going to have the Lewis base involved, plus the substrate with the leaving group. Whereas this one is only going to have the substrate with the leaving group as part of its expression. Okay, I mentioned this one already, molecularity. The molecularity tells you how the rate law is built. If it says 2 there, you have both components. If it's a 1 there, you only have one of them. So we can move on with that. Now, we'll digress just for a second. This introduces, I think in general chemistry, we get to the concept of Gibbs free energy in a discussion of entropy. Yeah. So remember, if the Gibbs free energy is a negative value, the reaction is spontaneous. But that, when we talk about Gibbs free energy in those terms, we're talking about this part and this part, and well, that's part of it. But we're discussing it in terms of equilibrium. Now we're going to use it in terms of kinetics. And this equation, which you shouldn't have to memorize or even use, it just demonstrates what happens to the K of an elementary step. That's the same K as in here. That K is dependent upon some proportionality constant. We call it fudge factors. That's just to make the units agree with each other. And then you have the Kelvin temperature. And then you have E, right, to the negative. Do better than that. Delta G of the individual step divided by the ideal gas constant and the temperature factor again. So what that says is, if free energy, and in this case, we're talking about free energy of activation. So here we're looking at this in terms of delta G. The free energy of activation now, as it becomes more positive, as it increases, which means more positive, then this value gets smaller. And if the rate constant is smaller, the rate slows down. So as delta G becomes more positive, the rate slows down. That's the whole point of that discussion. Let's see. This is just a graphical representation And the whole idea behind that is the energy barrier, as delta G gets bigger, the energy barrier increases. That means there are fewer molecules, whether it doesn't matter which one of these it is, there are fewer molecules that have enough energy to surmount that hump right there to get to the transition state. So we can also see that as T increases, K increases. So as we increase the temperature, now we have more molecules with sufficient energy to make the transition state. That just makes perfect sense. Right? You increase the temperature, you're putting more energy into the system. All right. We can devise a theoretical rate law. And if we look at elementary steps, we can use the elementary steps to devise the rate law for each one. I mentioned that earlier. You can do that for elementary steps if you have an equation to go from, like A plus B equals products. Then the rate law, based upon the elementary steps, will be derived from that. And then if you want an overall rate law for the reaction, then you have to meet certain conditions. In other words, the elementary steps that you propose, you have to add them together, and they have to give you the rate law that you determine experimentally. All right. So that's nothing new. I've already talked about the order, right? These are all ones because of the way the SN1s, SN2s, E1s, and E2s are built. They're all first order. All right. Now we're going to talk about stereochemistry. Oh, that reminds me. You guys didn't bring your models back, did you? Oh, thank you. You did?
I have to bring mine, but I'll bring it tomorrow.
Yeah, leave it at the desk. Okay. I thought I had a fleeting thought of sending you guys an email to ask you to bring your models.
I had mine on my desk at my house and I was looking at it today and I just had to throw it in here.
I was talking to you, huh? Yeah. It's kind of like that bag of candy bars when you go shopping. You hear his voice. Okay. Now, from our discussion so far, we're saying that SN2 and SN1 follow different mechanisms and they produce the same results. Well, overall, yes, they do. But there are stereochemical differences between the two. And that's another way that we can tell which one is the correct mechanism, by the stereochemistry that comes out of the reaction. So for instance, how would the stereochemistry of an SN2 reaction appear? If you've got two reactants, and I'm going to, rather than try to draw it, I'm just going to reference the slide. Notice here we have one chloro, one phenylethane with the chiral carbon has the chlorine attached to it. That's going to be the carbon where the nucleophile attacks. And it has an S stereochemistry. Sinister, that means rotates to the left. So the hydrogen's in the back. Chlorine is going to be number one. Then the phenyl group is going to be number two. And the methyl group will be number three. So it rotates to the left. And that gives us the sinister or the S stereochemistry. Now, how does that, in an SN2 reaction, we get both the attack and the leaving group at the same time. So how is that iodide going to attack that carbon? If the carbon is slightly deficient in electrons, then can it attack from the same side that the chlorine can? Right? The chlorine's coming out at us, right? So if it attacks from here, it's got two problems. If it's trying to attack that carbon, it's got this steric hindrance, that big chlorine sitting in the way, trying to get by. Plus, chlorine is electronegative, and iodine's got a charge. You got all these electrons out here, and there's electron repulsion. So as it tries to enter here, it gets repelled. So the natural way for the iodide to attack is from the backside. But if it attacks from the backside, now once it forms that bond and the chlorine leaves, the iodine's sitting on the backside where the hydrogen used to be. So now the stereochemistry is switched. So SN2 typically reverses stereochemistry. All right, if you have an SN2 mechanism, which is an elementary mechanism, if you have an S to start with, you end up with an R. If you have an R, you end up with an S. And we say that in that respect, that SN2 reaction is stereospecific. That is, it produces a specific stereochemistry. And this is illustration of a backside attack. The backside attack gives you what's called a Walden inversion. Think of it like an umbrella in a windstorm, right? He said, right, your stereochemistry is this way and the wind comes at you, it flips the other way. That's a Walden inversion. This just explains that what I told you before. The front side attack is hindered by both steric effects, things just physically getting in the way, and charge repulsion. So the front side attack, now Dr. Carty says it does not occur. I guess I'll take his word for it. I could imagine maybe 0.011% of the time it could occur, but he's the expert. Come on. There we go. And this just illustrates the both the steric hindrance and the repulsion. If it comes from the backside, you've actually got a slightly positive charge on the substrate. So the iodide would attack from the backside by attraction also. All right. What if we look at this one in terms of SN2 and say, what's the stereochemistry going to be? Well, the nucleophile is this hydrogen sulfide ion, and it's going to attack what? If it attacks from the backside, that bromine is going to leave, and now the sulfhydryl group is going to be facing away from us. I think this is probably one of the easier ones to reason. There we go. So when the sulfhydryl attacks, it puts it on the backside and hydrogen moves to the front. So the stereochemistry switches. Now, how about an SN1 reaction? In an SN1 reaction, you form the carbocation first. So when you do that, like I mentioned earlier, now the carbocation has an sp2 hybridization. It's trigonal planar. That is, it's accessible from both the front and the back. So you get a mixture of both stereochemistries. You get a mixture, even if it's an S to start with, you get some S's and you get some R's as a result. If the substance is pure, if you have a pure S, in this case, a pure S, then you get a mixture. If you've got a mixture going in, then who knows? I suppose you could get a graduate student to do that dirty work for you, but right, for doing it from a mixture. I don't know what the advantage would be. Is that cost? Because it costs a lot of money to stereochemically purify a product. So maybe you just want to go ahead and run your reaction and then purify it afterwards, rather than purify it twice. Okay, so that you would expect from an SN1 reaction to get a mixture of R and S from either the S as a substrate or the R as a substrate, either one. So here's the case where the chloride is leaving, right? It leaves behind an sp2 hybridized carbon, which is planar, and the chloride can attack from the front or the back. And there's the author's idea. Okay, now what can we expect? If the chiral center, that is the carbocation, well, actually the outcome of the reaction after the attack is generated from an atom that's not a chiral center initially, then both R and S configurations will usually be produced. So what's the ratio? Well, if the reactants in the environment are achiral, I mean, if it's not chiral to start with, and then you make it chiral during the reaction, you're going to end up with equal amounts of R and S around that chiral center. But if the environment or the reactant is chiral, and by that I mean I've deduced from other slides that the molecule can be chiral even if your carbocation is not, because once you form the carbocation, you're not chiral anymore because you only have 3 components. But if there's another chiral center somewhere on that molecule, then you're going to get unequal amounts of diastereomers, actually. So let's see what that looks like. Come on. There we go. Well, we got to introduce this idea. All right, in the SN1 reaction, when the leaving group leaves and you form the carbocation, sometimes the leaving group kind of hangs around, kind of pairs up. It doesn't reform the bond, but it's close enough to where it hinders access to one side. So if that's the case, and you can determine that from experimental results, right? If you don't get equal amounts, then you can suspect that maybe there's an ion pair in there restricting access to one side of the molecule. In this case, the leaving group is going to hang around on the side it leaves from. And that means the backside attack is preferred, even for an SN1 reaction. All right, so here we have an example of a molecule. I think it's got 2 chiral centers. Yes. The one that's not part of the reaction has the hydroxyl on it. That's a chiral center. And the original chiral center with the leaving group now becomes the carbocation. So you can attack from the front side or the back side. And you start off with an SS configuration, and now you end up with a mixture of SS and SR. So in that case, you don't have a racemic mixture, which you don't have 50-50. You have actually an unbalanced diastereomers. Remember, if you flip the R's and S's on every chiral center in your molecule, then you have an enantiomer because they're mirror images of each other, every chiral center. But if you only flip one of them, now you've made diastereomers. They're not mirror images of each other. Remember that part?
That was a while back. I remember the little stick figure guy, I think.
Yeah. So that's the point we're trying to make here. If it's chiral to start with, and it stays chiral during the process, right, with that, in this case, with that OH carbon, then it's going to be, you're going to have a mixture of diastereomers as a consequence. Now, are each of them equally likely? Right. So, these diastereomers are supposedly formed in unequal amounts. In other words, there's the proximity of the other chiral center will influence the attack, whether it's front side or back side. So in this case, the OH and the methyl groups are on the adjacent carbon. So depending on how remember how their Newman diagrams rotate them, the conformers, will dictate which side is preferred for the attack on that sp2 hybridized carbon now, carbocation. So with the top group, if the iodide attacks, well, okay. The A example creates a plane of symmetry through the phenyl group. And it's not symmetrical because you have an OH on one side and an H on the other of that plane. And the carbocation is in the plane. So since it's not a plane of symmetry, when it attacks, you get a diastereomer. And in the top possibility, the iodide attacks from the backside. And in the bottom scenario, the iodide attacks from the front side because it doesn't encounter the OH group that's in the way, right? That oxygen in the OH group is going to be electronegative. It's going to have an electron excess, delta minus, slight charge. So it's going to repel the iodide. So instead of a backside, it tends to make a front side attack. Well, the front side attack gives you, in this case, the 2s and 3r rather than the 2s and 3s. So you end up with a higher percentage from the front side attack, or the 2s, 3r. You end up with that one in excess. And the 2s's are lesser amounts. Okay, what happens here? Let's see, we're going to have, is it telling us SN1? Okay, SN1. So which one's going to leave? That's the question. What acts as the nucleophile? The iodide does. What best serves as the leaving group? The tendency would be to pick the biggest one, like the methoxy group. But in fact, the negative charge is more stable on the bromide. Largely because of its, well, two things, its size and its electronegativity are greater than the methoxy group. So the bromide, the bromine then represents the leaving group. So that means the carbon that it's attached to forms the carbocation. So the first thing you get is that bromine is leaving. right? So there it goes down there in the lower left-hand corner. I wish I had a bigger cursor. It's easier to see. So you form that carbocation. Now it's not a chiral center, but you do have a chiral center around the methoxy group. Okay, so when the iodide attacks, when the nucleophile attacks, it can attack from the front side or the back side. Well, with that, the way that's set up, that methoxy is in the back, right? It may be 2 carbons away, but it's still big. And it hinders the approach of the iodide. So the iodide is going to approach from the front side, the way we've got it written there, more likely than the back side. So the final at the very right, the diastereomer on the left is preferred. It's going to be the higher percentage outcome. Okay. Yeah, hot in here is just me.
I mean, it's regularly kind of warm.
Yeah. Okay. So with an E2, we're going to form a pi bond, right? If we've got a single bond, we're going to form a double. If we've got a double bond between 2 carbons, we're going to form a triple. In this case, we've got, and the reason we've got only a single bond between those 2 carbons in the middle is so that they'll rotate and give us different conformers. And we're going to look at the arrangement of the conformers to predict, to help us predict the outcome. Okay, so in this one, this 1s2r, 1-bromo, 1,2-diphenylpropane. So you got those huge phenyl groups sitting out there. And you got the, in the E2 scenario, we're going to take that one first. The E2 scenario, this all happens bimolecular at once. So the Lewis base, the hydroxyl, comes in, and it's aiming for that hydrogen sticking out there on number 1 carbon. All right, so when it takes that hydrogen, those electrons in that hydrogen carbon bond they're going to arrow over to the bond between the 2 carbons and form a double bond. But if you look at it, if you rotate it 90 degrees and look at it like this, what's the most likely conformation when the attack occurs? The most likely conformation is the one where the hydrogen is up here and the bromine is down there. They're anti to one another. Okay. That also puts those huge phenyl groups as far from each other as possible also. So that's why we end up with the E stereochemistry for this propene. All right. So there it is with the rotating around to the Newman projection. And this is, if you want to memorize a rule, the preferred attack in an E2 reaction is going to put the leaving group anti to the hydrogen attack. If we rotate it around where the hydrogen and the bromine are closer to one another in space, then those are the gauche attacks. And we call that anti-coplanar or anti-periplanar. For the hydrogen and the leaving group, their relationship to one another. All right. And this just hammers it home some more. I don't think there's anything more I can say about it. You do have both steric and, both steric and repulsive effects. when the base tries to attack. And this is still E2. Now, let me check my hard copy. Glad I got it out here. I'm expecting a discussion that we should have gotten. But it's not in the slides. Why is it not in the slides? Maybe I saw it in problems. You might see it in the homework where you have experiments 1, 2, and say 3, and you have a concentration of your nucleophile and the concentration of your substrate, and you change them, and then you have the rate. The rate of the reaction is determined over here. Right. So if you have a certain value here and a certain value there, and you get a rate here, then if you keep this one the same, change that one, or you say change both of them. I'd say this one is going to be now B, and then you go back to B here. Then with this one constant and only this one changing, if that's the case, and this produces an X, this produces a Y, but this produces another X, then only changing this one is the only thing that changes the rate, then that molecularity is 1. So it would be, if this were an SN type reaction, then this would be an SN1. But if you got changes, X, Y, and Z for all of them, then that means both rates are important and both rates have a bearing. Both concentrations have a bearing on the rates. And in that case, you have an SN2 or an E2. I must have seen it in homework or in the textbook. Yeah, I know I saw it in the textbook. So read up on that. Okay. This is the overall rule. So if you have an E2 reaction, it produces E and Z diastereomers. The diastereomer that is favored will be the one that's produced from the more stable anti-coplanar conformation. You can still get minor products of the Z conformation, right, where the hydrogen and the leaving group are on the same side, but it's a very minor concentration, less than 1%. All right. So what happens with an E1? Well, if it follows an E1 mechanism, first the leaving group is going to leave. Right? Rather than stay here, let's look at the mechanism itself. Here we go. So when the leaving group leaves, that leaves you with a carbocation, and you still get free rotation around that sigma bond. So the Lewis base is going to still attack that hydrogen, but what conformation are you in when it attacks? The conformation that is least strained is the one where those two big phenyl groups are opposite one another. So still you would end up with you're going to end up with a mixture, but you still have the minor product is the one with the most steric strain. So that being said, it's probably a little more difficult with the E1 and E2 reactions to tell from the outcome of the reaction which one is preferred, because you do produce both products, but the one with the greatest steric strain is the minor product in both cases. Okay, I think this is just a rehash, a reminder. Let's see. Where am I? There I am, there I am. Okay. Okay. I thought we still got some discussions to go. These SN1 and SN2 have been the simplest examples, sort of an introduction to multi-step mechanism. In fact, in this case, two-step mechanism, right? But reaction mechanisms can have many, many steps. And two of the most common that are added on to multi-step reactions are proton transfer and carbocation rearrangements. Right. We studied the elementary step proton transfer. That was first, the one that we first encountered. And then we looked at carbocation rearrangement, where you actually had a 1,2 hydride shift or a 1,2 methyl shift. Those are very common. But we need some guiding principles, rules, so to speak, to help us with our predictions. Right? And that's what these rules are for. The first one is fairly straightforward. You look at the environment for the reaction. Is it acidic or is it basic? And then you look at your proposed mechanism, and does it run contrary to the environment? Right? Say you've got an elementary step you want to put in there that produces a base, but it's in a strong acidic environment. It's not compatible. It won't be stable. The one that's stable is one where your elementary step produces an acidic product in the elementary step in an acid environment. So compatibility of acid base here is your first rule. Right. So the author says it better. Strong acids generally should not appear in the mechanism under basic conditions, and strong bases shouldn't appear in mechanisms under acidic conditions. And actually, that leads to the ability for the synthetic organic chemist to control the reaction, right? If the reaction can take place in either acidic or basic conditions, then you put it in acidic conditions to get one outcome, you put it in basic conditions to get a different outcome. And the proton transfer steps are very fast. And they're often used to make corrections, so to speak, in our mechanism. So we have to recognize, what do we mean by strong and weak acids and bases? Relative to water, is it strong or weak? Because now that's for aqueous environments, right? If you've got a non-aqueous environment, then you want to look at the solvent. What is its pKa? And then the strength of your acid is compared to that. But in general, the hydronium ion is considered a strong acid, and anything stronger than that is a strong acid. The hydroxyl is a strong base. Anything stronger than that is a strong base. Or you can look at the pKa. If your pKa is less than 0, that's definitely a strong acid. If your pKa is greater than 14, that is, well, I take that back. If the conjugate acid has a pKa greater than 14, then the base is strong. So here are some examples, strong acids, right? The hydronium ion, that protonated methanol, or a carbocation. Is that a strong acid? CH2. Yeah, it could be. Yeah, it's positive charge. So it could let go of its positive charge through proton removal. I'll go with that. Weak acids, water, ammonia, even ammonium is considered a weak acid. And then the methylammonium quaternary ammonium compound is also weak acid. Strong bases, there's almost nothing that beats the hydroxyl as a strong base. The NH2 minus, CH3 minus, H minus, those are all strong bases. Weak bases, water's both a weak acid and a weak base. Imagine that. Ammonia is a weak acid and a weak base. Ammonia?
No, whatever, like how water can be strong acid or strong.
Oh, amphoteric? Yeah. Chloride's a weak base. Bromine's a weak base. Iodide's a weak base. The hydrogen sulfate ion and the carbonate ion is a weak base. Okay. So what would happen here in this is basic conditions, right? You see the KOH there on the arrow, below the arrow. And the solvent here is DMSO, dimethyl sulfoxide. So we're not in aqueous solution. We do have a base. We're producing hydroxyl ions dissolved in DMSO. And the only reason I can think of that is because you don't want water side reactions. So we put it in DMSO rather than aqueous solution. And we want to end up with the nucleophilic substitution. So we're going to attack that hydrogen and form and create an ether, actually. So let's see what are the proposed mechanisms. Okay. Would it be wise for the hydroxyl on the, let's see, benzyl alcohol, that's what that is, attacks the carbon next to the bromine so the bromine can leave in an SN2 reaction? Well, what would that produce? Well, it would produce a strong acid in a basic environment. See, it's got that hydrogen. And then the proton transfer would be required. So that's not a valid mechanism. It's unreasonable because you're producing a strong acid in a basic environment, right? We need a different approach. So rather than that, we'll take the hydroxyl from the KOH and attack the hydrogen. So now, instead of the nucleophile being the benzyl alcohol, the nucleophile now is the hydroxyl. It attacks the hydrogen. It leaves us with a base in a basic environment. Now that base can attack the carbon that's attached to the bromine, and the bromine leaves, and we form a substitution of the bromine with the oxygen end of that benzyl alcohol. And that gives us the end product. That mechanism is more reasonable because we're not bucking the acid-base conundrum. Okay, now we have acidic conditions. So how are we going to do a nucleophilic substitution here? We want to replace that hydroxyl with a bromine. All right. So the temptation is to take the bromine. Let's see. Actually, what's the forbidden one? Oh, the heterolysis is the temptation here. The heterolysis would produce a strong base in an acid environment, right? Remember the heterolysis, we're going to break the bond with between the carbon and the hydroxyl. That would produce a strong base in an acid environment, and that can't happen. Right? It's unreasonable. Right? So we're not even going to go any further. What if instead of that, we let the hydroxyl be the nucleophile? It attacks the hydrogen on the bromine. Remember, these acids like that, these are covalent bonds. They will dissociate on their own. They will ionize on their own, but they need some help. So this nucleophile, the hydroxyl, attacks that hydrogen and forms the bromide. It also forms the, oh, what do I call that? I don't know what to call it. The oxycation. How about that? Then we can have heterolysis, where the water molecule leaves and forms a carbocation. Now the bromine, being the attacker, the base, the Lewis base, can attack that carbocation. Do a coordination step. It forms a bond. Remember, coordination is you form the bond with both electrons of the bond coming from one side. So we're going to coordinate with the bromine, and that forms the compound with a more reasonable elementary mechanism. This incorporates SN1 mechanism. Let's see. Yeah. Well, if you're told, are we told SN1? No, we're not told. We just assume we're going to do an SN1. Oh, because the outcome, excuse me, because the outcome replaces the hydroxyl with a bromine, we expect an SN type reaction. Excuse me. All right. That's the reasonable approach. Okay. How about a mechanism that this looks like an E1 or an E2, right? Because you're forming a double bond. So what's the leaving group going to be? Well, the product doesn't have a methoxy group on it anymore, so I assume that's the leaving group. But this is an acidic environment, so we can't produce a base in the process. Right? If we go through an E1 mechanism and we say, if we form this carbocation in an E1, right? The leaving group leaves first. That's an E1. So if the leaving group leaves, then what do you got? Well, you've got a carbocation. How does that help us? Right? We're in an acidic environment. Seems reasonable, actually. We haven't formed a base, have we? Well, yeah, we have. We did form this base. So I don't think that's reasonable, right? Because you formed this, look at that. You formed that base, right? In an acid environment. That can't work, right? So we need a different mechanism. So instead, this methoxy group is going to serve as the nucleophile. and it does a proton transfer from the sulfuric acid. Okay. And then it forms this oxycation. Right. Now we can let that leaving group go, and it doesn't form a base in an acid environment by heterolysis. Okay. Now that we have the water molecule can attack this hydrogen and produce another acid in an acid environment, and in the process form the double bond. So that three-step mechanism is more reasonable than the other. I know this is kind of, I don't know, it may be just flying right over your head. We're trying to use rule number 1 to decide between two different proposed mechanisms using the elementary mechanisms that we know. Okay. So this slide talks about the intramolecular versus the solvent-mediated proton transfer. The intramolecular proton transfer would be something like a 1,2 hydride shift. But that's allowed. What we're saying here is that there are two possibilities, right? The proton can either transfer itself from one atom to the other intramolecularly with the molecule itself, or the hydrogen can be transferred to some other molecule like that ammonia in the top, and then transferred back to the substrate. So how would that work? Well, if the ammonia is the nucleophile, right, it has the lone pair, where on the substrate will you find deficiency in electron density with one of those carbons, right? Because the oxygen is making a slight positive charge on the carbon. So if that attack occurs in an SN2 mechanism, then what does it produce? Well, it broke the bond between the carbon and the oxygen. So now we've produced a negative charge on the oxygen and a positive charge on the nitrogen. Now, how did it get from, and if we know the outcome, right, we know the outcome is 2-aminoethanol. How did it get from there using SN2? How do you go from there to the product, right? That's what that question is about. Because we have to get that proton off that nitrogen and onto the oxygen. So how do you get it there? It can't happen intramolecularly because it's too far away. Right? So it has to be an external transfer. You can't just go straight, right? You can't just go straight from that nitrogen 2 carbons away to the oxygen. That's too far. It won't happen. So we need an external proton transfer step. So when this happens, now that oxygen is going to take a hydrogen from a water molecule, and I assume from that we're in aqueous medium, it produces a strong base. Now the base goes in and it attacks the hydrogen on the ammonia and picks up the hydrogen from there. So it's not the same hydrogen, right? How do they know that? How do they know it's not the same hydrogen? Well, all you have to do is label it, right? Use deuterium instead of normal hydrogen. And you find that you end up with not deuterium in the final analysis, right? The hydrogen that's transferred is not deuterium. Right? So we need an external transfer of that hydrogen. It's not an external transfer of that hydrogen. It's a proton transfer of a hydrogen, not the hydrogen. Minor detail, I guess. All right. Oh, that was rule number 2. How did I miss that? Oh, avoid intramolecular proton transfers. All right, that's rule number 2. So rule number 1 is acid-base environment, right? Match those up correctly. Rule number 2 is avoid intramolecular proton transfers. If they're not on adjacent carbons, then you're not going to get that happening. So you need external transfers. All right, rule number 3, avoid termolecular steps. Remember kinetics in general chemistry? The most likely to occur are the unimolecular, because you've only got one molecule. The next most likely is bimolecular, and you still have to get them coming together with just the right energy and orientation, right? So when you try to do that with 3 molecules, the probability of getting the right energy and the right orientation goes way, 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 way down. So we just say avoid termolecular steps altogether. Don't try to do three reactants and flipping their arrows around like this step does. Now, that goes back to that 3-error rule too, because you're unlikely with a termolecular step to be able to get through it with 3 arrows or less. So if you keep the three error rule as your maximum, then you're automatically going to avoid termoleculars. Right? That will never happen. So the way it's described it. So now why are we throwing this one in here? Avoid termolecular steps. Okay. Carbocation rearrangements. Maybe this is just a reminder. Oh, I see. If we're going to go through an SN1 reaction, then the iodide is the leaving group, right? So it would produce a carbocation where? On that secondary carbon, right? Let's see, we've got right, methyl iodide here. Okay, if this is an SN1 and we're going to substitute a hydroxyl for it, then the SN1 says first thing that happens is that iodide leaves. Right? What does that leave behind? We've got that, plus we've got this one. Oops. I want an X on the plus. There we go. We got a carbocation on a secondary carbon. It would be more stable on this tertiary carbon. Tertiary is more stable than secondary. So why don't we do a methyl shift? Right? Here we go. Or actually a hydride shift. Yeah, that would be better. Right? Because we do have a hydrogen here. Actually, it's in the back, I think. We have a hydrogen here. So if we move that over there like this, now we've got that hydrogen and a methyl group here. This is more stable. So if we do that 1,2 hydride shift, we get a more stable carbocation. And then when the water attacks, the water being now the nucleophile, excuse me. We form a bond here. And then the hydrogen is picked up in a proton transfer by water. Now this would have to take place. How would this take place? Would this be an acid or a base environment? No, because you're producing iodide, right? It would have to be a basic environment with water. But then if it produces okay. There's possibility that, well, I'm sure this occurs. I just can't reconcile it with our rule number 1. That's my problem. Because we're producing this hydronium ion. If it's a basic environment, that hydronium is going to be, right, it's not going to be stable. All right, so something else is acting here, which I can't help you with right now. Okay, rule number 4. All right, I think those 2 slides were setting us up for rule number 4. And there are only 4 rules at this stage of the game. A favorable 1,2 hydride and 1,2 methyl shift will usually win. If an energetically favorable 1,2 hydride shift or 1,2 methyl shift, come on, okay, competes with another possible elementary step, the carbocation rearrangement is usually faster. What does that mean in terms of energy? If it's faster, it means it has a lower threshold energy, activation energy that it has to surmount. All right, so what product should we get out of this reaction? If it's an SN1, the bromide leaves, and we've got an ethanol, right? That's what that compound is. An ethanol serves as the nucleophile, excuse me. Where is it going to attack? We're going to get a 1, 2, 3, 4. This has to be a methyl shift, 1,2 methyl shift, in order to give you the carbocation on that tertiary carbon. Plus, notice we got that phenyl group hanging out there. That will also stabilize it. Stabilize the carbocation being that close to a phenyl group. Right. So let's see. If we get this intermediate carbocation, there it is. All right. A hydride shift would not stabilize. All right. Okay. So what Carty is trying to show here is that a hydride shift in that first step would actually destabilize the molecule because it would move the carbocation to a primary carbon from a secondary or a tertiary carbon. Right. So instead, we get a methyl shift. The methyl shift places the carbocation on the first carbon attached to the phenyl group. And that delocalization, resonance delocalization, stabilizes that carbocation even further than the tertiary carbon. Then the alcohol can attack. And what we end up with is an ether. Whenever you get the possibility for a resonance stabilization, go for it. In this case, we're going to This is a type of mechanism is this? It's not elementary. The substitution doesn't take place on the same carbon as the leaving group. The leaving group would be hydroxyl, right? But the chloride is not attached to that one. The chloride is attached to the other carbon. And so what's happened there? Well, let's see. How do we explain that? Oh, we're told it's an SN1 mechanism. Okay, so the leaving group leaves first. So we get a proton transfer first, and then the leaving group leaves. So we get water leaving. Okay. That produces a carbocation on a actually a tertiary carbon, but it's more stable if you can resonance stabilize. In other words, we get both structures, right? The tertiary carbocation and the primary carbocation through a methyl shift. And when we do that, actually it's resonance stabilization, not a methyl shift, excuse me. We stabilize the structure by offering the molecule more possible conformations. If you can delocalize electron density throughout a molecule, you stabilize it. So this resonance ability, by moving the carbocation backwards and forwards between the tertiary and the primary carbon, you have the opportunity to produce the chloride attack on a primary carbocation. Now, I'm looking to see, it says it's 96%. Okay. Why would it be? I mean, if the carbocation is on that primary carbon, why would it be the 96% preferred site for the chloride attack? I'm thinking steric hindrance. Yeah. I mean, it could attack front side or backside on that carbocation on the tertiary carbon. But still, if it's a primary carbon, it can attack from any side, all around. It's got nothing's in the way. That's the only thing that makes sense to me. Not being,
Why that's so high.
yeah, that's why I'm thinking it's so high. At least that's the way an inorganic chemist thinks about it. If I were a trained organic chemist, maybe I'd have another explanation, but that's the only thing that makes sense to me now. Okay. So hold on a second. There's the explanation. All right. Hold everything. Dick Tracy calling headquarters. Remember those old cartoons? You don't. They're too old, right? Okay. So the structure is stabilized, but we're still preferring the tertiary carbocation. And the chloride, well, the mechanism says it's attacking that the primary carbocation. That doesn't make sense. Go to the second. Oh, when it does attack that one, then it allows the coordination bond to form and the movement of pi electrons into the position between the two carbon atoms. It's a little hard for me to grasp.